All right, ladies and gentlemen, I do apologize for not recording the first part of this. The beginning part of class, we went a super fast review of electron configurations and quantum mechanics, all of that wonderful stuff. And then we made it up to this problem, which is on the back side or the second page of this electron configurations worksheet. Since you all have the key, I just was to kind of wrap this up. Are there any, do y'all have any questions about number 6 or number 7? Anything you wanted to look at a little more closely? Okay, so since I'm not hearing any questions, we'll go ahead and wrap this up. Feel free to ask me. I anticipate that I will be here Friday and Monday. Dr. Weber was given instructions that the trial will probably wrap up. Monday will probably be the last day of the trial. So, of course, who knows how all of that stuff goes. You know, they could decide to settle out of court tomorrow, but I should be here the next couple of days, next couple of class periods. If you all have any remaining questions about these, feel free to ask. So what I would like to do next, I would like to switch over to there we go. That's what I was looking for. Lewis dot structures. That's the one. Okay. We're going to take a quick look here at Lewis dot structures. All right. So some of our big objectives here. We want to be able to distinguish covalent bonds versus ionic, which I think y'all have done previously. But now we want to add a layer of sophistication to that and talk about polar versus nonpolar. Both polar and nonpolar are considered covalent bonds, so they're still going to involve sharing electrons, but it's a little bit more complicated than that. If there's any message you take away from this class about chemistry in general, it's always a little more complicated. I had a student a number of years ago that came up to me at a social function the department was having. He was like a senior level chemistry major, and I'd had him for general chemistry, and he came up to me, he said, Dr. Patterson, I am so mad at you. I was like, what did I do? And he said, you lied to us. And what do you mean I lied to you? And he just started listing off all of these things that we teach in general chemistry, that when you're taking senior level chemistry, you realize there's so much more to the story. So it's not that we're lying to you, it's that we're doing our best to figure out the rules of the game. But we didn't write the rules, right? We didn't create the rules that electrons follow. And so we're just doing our best to figure out what those rules are and then try to communicate them to you. But there's always more to the story. And so we've taught you about ionic and covalent bonds. Now we're going to shade covalent bonds into polar and nonpolar. We're going to talk about something called electronegativity, which measures how atoms interact with each other when they have a covalent bond. And we're going to look at reading Lewis dot structures, which you already did a little bit way back at the beginning with combustion reactions. And we're also going to be looking at creating these Lewis dot structures for both molecules and polyatomic ions. Okay. Wow, I hope I still am recording. It used to be with Zoom when you're recording, it had a little red dot, and I'm not seeing that little red dot right. No, that's PowerPoint. That's not. Oh, here, this is what I was looking for. Yeah, it says pause or stop recording. So yeah, we must be recording. That is good. Okay, so quick review here with alkanes where we saw Lewis dot structures before. Methane, propane, we're looking at compounds that belong to the family of hydrocarbons. They're made up entirely of hydrogen and carbon. these two names are really similar, right? They both end in A and E, methane and propane. What do meth and prop tell us? Yeah, the meth and the prop tell us carbons. Meth means one carbon, prop means three carbons. And so this family of alkanes, they have this chain of carbon atoms as the backbone, and then we fill in hydrogen atoms so that all the carbons have four bonds. And that determines how many carbons and how many hydrogens there are. It gets more complicated. Sometimes these chains of carbon atoms can, as the chains get longer, they can loop back on themselves and close and make rings. And that's what we have here with this compound aniline. We also have some double bonds thrown in there, and we can have other atoms, not just carbon and hydrogen. There are all sorts of other atoms in the periodic table. It's going to be non-metals that we make covalent bonds with. So the elements that you see in these Lewis structures are going to be non-metals for the most part. So why in the world would bonds form between some atoms? Well, this huge principle in the physical world is to go to positions of lowest energy. It's like if you let go of a ball, it's going to fall to its lowest gravitational potential energy. You let go of a ball on a hill, it's going to roll all the way down to the bottom of the hill, right? It's this minimizing energy is the thing. So we want to get to this lowest energy level possible. And if this collection of atoms can form bonds in such a way that the overall energy is lower with that bond than without it, the atoms are going to form those bonds. Okay. Then this octet rule. So with the octet rule, this is going to be a guideline for what a stable arrangement of these electrons is. The atoms want to have 8 valence electrons around themselves. On the electron configuration worksheet on that second side, question number 6, if you take a look at the isoelectronic one, they all have 8 valence electrons. Because those 8 valence electrons are a particularly stable arrangement of electrons, particularly low energy. Atoms can get that octet of electrons basically 2 ways. They can get it by giving away electrons or by taking extra electrons. We can refer to that as transferring electrons. That's what happens with ionic bonding with a metal and a non-metal. Or if we're making a covalent bond, the atoms can share electrons. And so either way, whether it's by transferring electrons or by sharing electrons, they're trying to reach these octets. That means that the S and the P subshells in the valence shell are completely filled. 2 electrons in the S, 6 in the P, and that arrangement of electrons looks just like a noble gas, right? Neon, argon, krypton, xenon, radon, those guys don't do chemical reactions because that electron arrangement is super, super stable. There's no advantage to sharing or transferring electrons if they already have that octet. So for the next one, we've been talking about ionic and covalent bonding. Sorry, I think I left my email open on this. I don't want to share my email, so I'm not gonna step out and close that. Sorry, not unless it starts dinging a whole lot. On this concept of bonding, we were talking about ionic bonding and covalent bonding, which are the 2 extremes, right? We've got ionic bonding over here and covalent bonding over here. We've been talking about sharing electrons versus transferring electrons, but there's another possibility that lies in between that, which is unevenly sharing electrons. This is what happens when you get 2 different nonmetals together. So if we have the same 2 nonmetals, like green is often used to indicate chlorine. So I would interpret this molecule farthest to the left as being Cl2. It's one of the Brinkelhoffs, or these elements that always exist, 2 atoms stuck together. So in chlorine, each chlorine atom pulls on that shared pair of electrons making that covalent bond evenly. And if they're pulling on it evenly, they share the electrons evenly. But over here in this middle one, the bigger atom on the right, which is probably going to be chlorine, being that greenish color. Not sure what atom they'd be talking about over here. Maybe something like hydrogen. Hydrogen doesn't pull on the electrons as strongly as chlorine does. So that means that the electrons spend more time in the orbitals of the chlorine atom than they spend in the orbitals of the hydrogen atom. So they're unevenly sharing it. You may have some sort of arrangement in your life where you're supposed to be sharing something, but it's not really an even share. That used to be a friend of mine and the TV remote control. We were sharing remote control, but somehow my friend seemed to have the remote in his hand a lot more often than I had it in my hand. So when we unevenly share the electrons, it just means that the electrons are found more often in one atom's orbitals than in the other atom's orbitals. And then the extreme case of that is in the ionic bond, where one atom pulls on those electrons so strongly that the electrons completely leave the other atom and go to that atom that's pulling on them really hard. So this unevenly sharing is sort of an intermediate state between evenly sharing and transferring. The way that we measure how likely the electrons are to transfer or to be shared is with a property called electronegativity. And that's what this EN stands for at the top. Let me take a peek at my next slide. Yeah, okay, so ready to go there. Electronegativity is how strongly an atom pulls electrons towards itself when it's in a chemical bond. And it's something that we call a periodic property. Now, I'm going to do a little marking up on here using the mouse. I can't find my tablet, as I mentioned at the very beginning of class. So my writing with the mouse really stinks. So I apologize for that in advance. But being a periodic property, it means that we can look at an element's position in the periodic table and make some assumptions about how big or how small that property is. And in the case of electronegativity, the atoms that exist in this corner of the periodic table have the biggest electronegativity. So I usually draw arrows like this. And I guess I need to write in one more word because different textbooks draw these arrows with different meanings. So I'm going to also write in the word big. The arrows point in the direction of the biggest electronegativity. So when we're comparing two atoms, we can just see where they are in the table. And the atom that's closer to the upper right corner has a bigger electronegativity. The one farther away has a smaller electronegativity. And I'm also going to cross out the noble gases. I think if you think of, whoops, I crossed out astatine too and didn't mean to do that. I think if you think about the definition of electronegativity for a moment, you'll realize why I crossed out the noble gases. Try that again with staying in the line there. Okay. So the definition of electronegativity is how strongly an atom pulls electrons towards itself when it's in a chemical bond. What do we know about noble gases and chemical bonds? They don't bond. So we don't really measure electronegativity for noble gases. Now, this is one of those places where I'm flat out lying to you. A guy named Neil Bartlett won the Nobel Prize for making compounds with noble gases. The noble gases can do reactions, they can form bonds, but generally speaking, they don't. So we tend at this level of chemistry to just ignore noble gases, but I don't want to be lying to you. So we're going to cross them out. We're not going to talk about it, but just know that that's one of the places where there's some really rich, really cool chemistry to learn about in a junior, senior level advanced inorganic chemistry class. Okay, so, how are we gonna use this? Oh, I didn't have any examples. Okay, sorry. I think I'm gonna switch over to the document camera and we'll just do a couple of examples, like what you might see on a homework or on a quiz or a test related to electronegativity. Stop this share. Let me go over to advanced, second camera. Okay, so questions you'll see specifically about electronegativity on a quiz or a test tend to be questions like rank these elements from smallest to largest electronegativity. And the elements that you get might be something like, let's throw in germanium and cesium, the fluorine and sulfur, something like that. So when you're taking the test, you're going to have a periodic table. So go find these elements on the periodic table and mark where they are. So on your periodic table, the biggest electronegativity is going to be in this corner, the upper right. We've got germanium, Ge. Germanium is right here. We've got cesium, Cs. That's going to be down here. We've got fluorine, it's the upper right corner. And we've got sulfur, that's also towards the upper right corner. So if you've got those marked, the biggest electronegativity is closest to this corner, that'll be fluorine. The smallest is the farthest one away. So cesium, germanium, sulfur, fluorine would be smallest to biggest electronegativity. The answer to that is it depends. So if we're getting that, when we start getting elements really close to one another, you probably want to look at a table, like a periodic table that has the numbers for electronegativity written in on it. For these types of questions on a test where they aren't giving you numbers, we're just expecting you to look at that overall trend. And so, you know, another way that that question might be asked is I might give you like, I might give you 4 elements. Like I'm gonna mark these in purple. That doesn't really show much differently. Do I have a really different color? Not really. Well, maybe the expo marker will write a little differently. Yeah. So we've got an element here and an element here, an element here and an element here. So I might ask you, say, out of those 4 elements, which one has the biggest electronegativity? And then you would pick the one that's in the upper right corner out of that square. Right, so we'll be going for the big overall trend. If you look at the actual numbers that go with the electronegativities, you're going to find all sorts of exceptions to this overall trend. So if you're given numbers, use the numbers. If you're not given numbers and you're expected to use the periodic table, we're just going with the overall.
Well, like for this chemistry class, will we see a specific metric? Just more we're currently like in a broad area.
Yeah. Yeah. Because what we'll be interpreting is that if 2 atoms are bonded to each other and they have a relatively small difference in their electronegativity, it's going to be what we call a pure covalent bond with even sharing of the electrons. If 2 atoms have a bigger difference in their electronegativity and they're both nonmetals, we're going to call that a polar covalent bond. Because the one that's closer to that upper right-hand corner is going to really be pulling on those electrons much more strongly than the other. where the electrons are spending more time, they're gonna make that end of the molecule a little bit negative, and it's a big enough effect, we can actually see it experiment. And so, we're doing this very much qualitatively. Is it polar? Is it non-polar? Is it ionic? If the difference in electronegativity is really big, then it becomes an ionic bond. And there are huge correlations with these things. Big differences in electronegativity and ionic bonding happen when you have a metal and a non-metal bonded to each other, right? Which is what y'all were told weeks ago is an ionic bond, metal plus a non-metal. Covalent bonds, non-polar and polar, the difference in electronegativities fall in the ranges of things that are non-metal. And specifically, non-polar covalent bonds are going to be two of the same atom bonded to each other, like oxygen to oxygen, where you have a difference in electronegativity of 0. So they're pulling exactly the same on the electrons. Or there's one huge exception to that, which is carbon and hydrogen. There is a slight difference in electronegativity between carbon and hydrogen, but it's so small, you don't really observe it. So we consider carbon and hydrogen to be nonpolar, and any bond of the same two atoms, same two non-metal atoms, nonpolar. Any other non-metals bonded to each other are going to be polar, except for carbon and hydrogen. Okay, so that's what those questions, whoops, don't want to mess with that. I want to mess with this. I want to stop sharing. Oh, that's right, because I'm not sharing. So what I'm going to do is just share. Okay, what do we have? Okay. So crickets are good luck.
Sure.
Always happy to have a cricket. All right.
But
Crickets I'm happy with, roaches, I will admit.
thanks, Brad, I knew that feel.
Okay,
Yeah.
that'll be fine.
Alright.
So, back when you all were looking at combustion reactions and you're looking at alkanes and hydrocarbons and all of that, we had some of the vocabulary that goes with Lewis dot structures. Single bonds are formed when you have one pair of electrons shared, something like HH here. That pair of electrons is referred to as a bonding pair. If you have two pairs of electrons, we call that a double bond. We also can have in something like oxygen, we have what are called lone pairs. Lone pairs is kind of an older term. It seems like experts these days are calling them non-bonding pairs. Non-bonding actually comes from quantum mechanics. So I guess at some point, somebody might as well call them what are best electron theory calls them. So yeah, those electrons that are stuck on the end of oxygen that are just on one atom are called non-bonding or lone pairs. And then if we share 3 pairs of electrons, we call that a triple bond. And we can draw 2 dots. 2 dots are equivalent to 1 line. We only use the line notation for bonds. We don't use the line to represent a lone pair. The lone pairs are drawn as dots. Bonding pairs are drawn as lines. So yeah, quick check on this one. How many lone pairs and bonding pairs are in ozone? I'm showing you down at the bottom 2 different representations of ozone. One is all dots, the other is a mixture of dots and lines. So count just for one of the representations. How many lone pairs and how many bonding pairs do we have? Yeah, I would agree with that. 6 lone and 3 bonding, right? So the lone pairs are going to be the ones that are out like this, right? So those, all of those that are not shared between 2 atoms are lone pairs. So that's a grand total of 6 lone pairs. And then the bonding pairs, I'm gonna mark with arrows. We've got 2 pairs right there with that first arrow, 1 pair right there. So 6 lone, 3 bonded. Any questions on that? Just keep in mind the octet rule. Atoms want to gain, lose, or share electrons till they have 8 electrons around them. And when we're talking about this, I guess that last slide should say valence. They want 8 valence electrons. This procedure for Lewis dot structures, it's a lot of words. And if I go through the procedure right now, it's just meaningless reading a bunch of words. There's one thing I want to point out though, before we start drawing them, because I think it's easier to start drawing them and then come back and look at the procedure. But one thing I want to point out is step 1 and step 2. Those 2 steps are independent of each other. So it doesn't matter if you count electrons first, or if you come up with the backbone of the molecule first. But 1 and 2 have to both be done before you can do step number 3. So the 3 big steps here, we count valence electrons, we come up with the backbone or how atoms are connected to each other. And then the 3rd step is we put those valence electrons into the backbone. So let's see. I think what I need to do here is move over to the document camera so that I can draw these. So y'all bear with me for a moment. I just want to see what all of the compounds are that I have to do. And then I'll go back and do them on the document camera. So we're going to do methane. We're going to do carbon tetrafluoride. Do formaldehyde, do nitrogen, do nitrates. All of this is introducing various facets. Okay, and then we're at polyatomic ions. All right, so I'm going to go back to here, and I'm going to stop sharing and go back to the document camera. And then let's advance the camera. Okay, there we go. All right. So methane. What is the chemical formula for methane? Almost.
CH.
CH4. C3H8 would be, what would it?
Propane.
3 is propane. So yeah, CH4, that's going to be methane. Okay. So if we're going to count valence electrons, we're going to need a periodic table. We did not review this earlier in class today. To find valence electrons from the periodic table, we want to look at the last digit of the group number if we're in the S block or the P block. And carbon and hydrogen are in the S and the P block. Carbon is in group 14. So it's going to have 4 valence electrons. And hydrogen is in group 1. So it's going to have 1 valence electron. We just take the last digit of that group number for valence electrons. So carbon, we're going to have 4 valence electrons. Hydrogen's going to have 1 valence electron. And the way I normally do this, I like to see this if I'm checking students' work. And it's a way just to double check that you didn't have a math error on this. What I normally do is I take the number of valence electrons, and the subscript, and we multiply them times each other. So carbon, there's 1 carbon, and the periodic table says that it has 4 valence electrons. So that's all for carbon. And then we're going to add to that the fact that we have 4 hydrogens, and the periodic table says that each hydrogen has 1 valence electron. And so if you add all of that up, you get 8 valence electrons. That first, annotate that with a different color. That first number, the 1, is the subscript. And the second number is the number of valence electrons for the element from the periodic table. We're just looking at the last digit of the group number. So we've got 8 valence electrons. So back on that long list of procedures, that was step number 1. We wanted to get how many valence electrons are in the molecule. Step number 2 is figure out the backbone. There are a lot of things to figuring out the backbone, lots of different ways of approaching this. I think the simplest for a molecule like this, if you have one of one element and you have multiple of another element, the thing you have one of is going to be in the middle. The thing that you have multiples of is just going to be arranged around it. Formally, we say that the least electronegative element will be in the center, surrounded by the other elements, except hydrogen can never be a central atom because hydrogen's this huge exception to the octet rule. It only wants 2 electrons because with hydrogen, its single electron is in the 1s subshell. And if it gets one more electron, the 1s subshell is totally filled and it looks like helium. So hydrogen wants 2 electrons, whereas everybody else to look like a noble gas needs 8. So in this case, with carbon and hydrogen, we're just going to put carbon in the middle, and we're going to put the 4 hydrogens around it. With Lewis dot structures, we normally keep it sort of on a square grid. Just we put things to the left, to the right, above and below. Once we have that structure, and we know that there are 8 electrons, we start putting those 8 electrons into the structure by gluing the atoms to each other. That's the first thing we want to do. So if I'm going to stick all of these hydrogens to the carbon, I'm going to do it with pairs of electrons. So that's 2, 4, 6, 8. I just used up all my valence electrons. To be a good Lewis dot structure, every atom needs to have 8 valence electrons, except hydrogen, it needs to have 2. We double count the shared electrons for both atoms. So the shared electrons get to count for carbon towards its octet, and the shared electrons get to count towards hydrogen for its duet or 2. So if we're going to count how many electrons are being shown on carbon, we would count those. It has 8 electrons being shared. And running out of markers. Oh, I wonder if this will show it. I have 2 very light colored markers. Maybe one of these will show. For hydrogen, for counting its duet, we're going to count those. Right, so it's the, oh wow. The document camera is picking up a very light pink is a pretty strong red. At least to my eyeballs, these look very different. One of those hydrogens has 2 electrons adjacent to it. The carbon has 8. This is a good Lewis dot structure. Everybody has an octet except for hydrogen. All the hydrogens have their duet. Do you have any questions on that one? Okay. Let's try the next one. The next one says carbon tetrafluoride. What is the formula for carbon tetrafluoride? CF4, right? I love the binary covalent nomenclature because the prefixes tell you what subscript to write. You don't have to think about it, right? If there's no subscript, you don't write one, or if there's no prefix, you don't write a subscript, it's just the 1. And then when it says tetra, you just write a 4 and life is good. Okay, so in this compound, we have 1 carbon. And in the previous problem, we said that carbon has 4 valence electrons. That's finding carbon in the periodic table and looking at the last digit of the group number. So 1 times 4, that's from the carbon. And then we have 4 fluorines. And fluorine, I squiggled out here, fluorine is in group number 17. So it has 7 valence electrons. And so we've got fluorine. So we've got 1 times 4 plus 4 times 7. That's 4 plus 28. That's going to be 32 valence electrons. In terms of the structure, we have 4 fluorines, 1 carbon. We'll put the carbon in the middle. We'll put the 4 fluorines around it. So this is looking very much like methane, just with the fluorines swapping out for the hydrogens. Those 32 electrons, when we go to put those 32 electrons into the structure, we're going to start gluing the atoms together. So we'll put 2, 4, 6, 8. Once we have the atoms glued together, the next thing is to make sure that all of the outer atoms have octets. So I'm going to go back and try to put 6 more electrons on each of the fluorines. I've already used 8. That'll be 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. So that uses up all 32 valence electrons. Does carbon have an octet? There are 8 electrons associated with the carbon. How about fluorine? Does fluorine have an octet? Do all 4 fluorines have an octet? Yeah. So the fluorine octets look like this. So this is a good Lewis dot structure. I want you to try the next one. The next one is formaldehyde, which is CH2O. Figure out the backbone, figure out the number of valence electrons, see how you can arrange them in. Give you about a minute to work on that, and then we'll reconvene. The 1:40, so we got about 3 minutes, but 1 minute to work this example. Probably a good one to end on. I realize that may not have been enough time, but let's do this as best we can for the next, well, till 1:40. How many valence electrons did you calculate?
2.
22? I, 12? Okay. So,
Oh, I didn't take the last digit, I took the whole digit.
yeah, last digit of the group number. There's 1 carbon with 4 valence electrons. There are 2 hydrogens, each with 1, and then there's 1 oxygen with 6. Right. So 6 and 4 is 10 plus 2 more, 12 valence electrons. Which element should be in the middle? Carbon is going to be in the middle. Here's why. hydrogen never in the middle, because it's only gonna make one bond to fill that one S2. So that leaves carbon and oxygen. So here's where carbon and oxygen are on the table, the least electronegative. The one with the smallest electronegativity will go in the middle, so that means carbon will be in the middle and oxygen will be on the outside. So we'll draw carbon, we'll draw an oxygen, and we'll draw two hydrogens. Now, all four positions, top, bottom, left, and right, are considered equivalent, so it doesn't matter where you have the blank. Your arrangement around carbon may look different than mine. We just want one oxygen and two hydrogens around it. If we glue the atoms together, 2, 4, 6, okay, we use half of our electrons. The next step is to make sure all the outside atoms have octets. Hydrogen wants duets, so it's good right there. So we'll take those others, and that makes 8, 10, 12, and we'll put them on the oxygen. What's wrong with this structure? Carbon has 6, it wants 8. We have that blank spot on top. We can't just make up extra electrons and give to it. But what we can do is we can take a lone pair from a neighboring atom and move it to be a shared pair. So we can take a pair of electrons from this oxygen, because that's the only place we have lone pairs, and we can move that lone pair into being a shared pair. And when we do that, we end up with a structure like this. Hydrogen bonded to carbon, there's a hydrogen. Now let's look at the oxygen a little more closely. We're going to take that lone pair and move it in. So now there's a double bond between carbon and oxygen, and we still have 2 lone pairs. And if we do that, both carbon and oxygen have an octet. And so that would be the Lewis dot structure of formaldehyde. And we are out of time, I am sure. We are 2 minutes past. All right. Thank you all very much. And we will pick up on Friday. In the meantime, let's see if I can turn off the recording. Oh no, don't tell me. Don't tell me I quit recording at some point.
Sure.
Oh, there it is. There's the recording. That's stop recording. That's pause. Okay, there we go.